everybody. Thanks again for being here. Coffee nor coffee, we are going to be awake for this session. This is our last but not least our presenter, Yildirim from Wichita State University. And this is the last talk for the factory operations module. Shortly after following the talk, we're going to talk about collaboratively, what are the major issues or what are the common issues that we want to talk about. But with no further ado, here's our speaker.
That side so that you don't have to turn both sides.
Okay. Thank you for being here. Today what I will do is I will go over a very short informal review of energy-aware operations planning. Before I do anything else, I would like to share something, a slide about a small study that we had for a senior design project in a small manufacturing company in Wichita, Kansas. That was probably around 2006 that we did this study. And in this shop, which had 4 CNC machines, which was the bottleneck area for the whole plant, we observed that around each machine is at least 16% idle, or some of them are about 68% idle, which was corresponding to 13% of waste energy to 62% of waste energy. So this motivated us to our current research stream. So what we did immediately after this observation was getting a data logger and try to characterize energy profile of a machine. So with a portable power cell. So that was what we did. And essentially, if you take a look at here, I removed all of those variations. Whenever you turn on a machine, it takes some time and some energy. When the machine is idle, again, there is some power consumption. When machine is working on different jobs, definitely they consume energy. But when you try to turn off the machines, again, there is another spike where you have consumption. If you want to turn off and turn on a machine, then it requires a certain amount of time. Another observation that we had was for a single machine, with all of the subsystems that you have, only around 20% of the actual work goes into the part. I mean, we had some experimental design, and this was consistent on a CNC machine working on some titanium parts. So this gave us the motivation for our study. And most of the things that I will be presenting today are on the deterministic part. Almost everything, I have put everything under energy-aware operations planning umbrella with 2 major branches. One is energy-aware production planning. The other one is about peak load management, production planning for peak load management. In the first branch, what you have as input, you have energy profiles for different machines. And then you have some information about demand, job characteristics, due dates. And what we have done is we have created, or anybody who has been in this area, have some mathematical models, most of the time multi-objective models, either on a single machine or on multiple machines in different setups like parallel machine, group technology, flexible workshops, etc. And the final result is some feasible schedules and a Pareto front with respect to different objectives that you have. And energy consumption is usually one of the objectives. With this, what you try to obtain is when should you turn on or turn off the machines? How long should the machines be idle? And how should you schedule jobs in the production system to optimize your objectives? And at the end, if you have the Pareto front, then which solution do you implement? For peak load management, again, you have energy profile and demand job characteristics in a multi-machine environment. But this time, what you want to do is you want to minimize the facility demand. What is the reason for that? Because if you are a manufacturing plant, at the end of the day, when you try to pay for your bill, you have two kinds of charges, major charges. One is the amount of consumption that you have, and the other one is the demand charge. Demand charge is essentially the capacity that utility provides to you, and they claim that they have to charge this over a 1-year period, although they observe that demand over only a 15-minute period. So if you are a plant, if you are not smart, turn on everything at the same time just for 15 minutes so that you can see if all of your systems are working, then you may be penalized for that for the whole year, a big penalty. So most of the research in this area is in these two categories. What can be done to extend this research to other dimensions? I mean, not that when everything that I have in purple, I mean, it is new research directions that I think we should go over. And again, I am talking on the deterministic side, on the stochastic side. All of these have avenues as well. So considering both objectives, how do you synchronize? How do you plan for multiple production lines that you have in a plant? Or how do you incorporate non-process energy like HVAC or lighting or heating, ventilation into this problem? So we are just increasing number of systems that we have. Yesterday, one speaker was talking about systems of systems of systems. I am going from the smallest system to the larger systems that we can investigate. So this is one plant. What if for that plant you also plan for some smart grid technologies, some other avenues which you may take advantage of, like storing energy by different means, batteries or thermal storage, or so many other ways to store exist right now, or generating additional energy. Why is this important? Especially if you have real-time prices and if you can come up with a way to sell your excess energy to utilities. Look at here, the price of a megawatt per hour. This was on 7/18/2013. Regular price is at the bottom, probably 10, 20-ish. How much is here? Around $500. If you know ahead of time what is going on, there may be some opportunities for you. You may want to say that, okay, I am turning off everything that I have at the facility, just let me sell the energy. Or the usage rights of the energy that I have. Maybe that will make more money for that particular day, even for small manufacturing companies. Or if you have several companies, do all companies need to make the same investment, or can they come up with a central facility? I mean, I think that was also a point that was made yesterday for regular buildings. So the same problem when you have many facilities, many companies, but again, how do you share the resources? How do you price usage of resources? How do you plan together? I mean, those are very difficult problems to solve. Let's put one more dimension into here. Networks of smart grids, not only electricity, but also maybe have the gas network being there. I mean, if you are in Europe next year, I'm sure if Russia does something with the natural gas, there will be lots of demand response for gas consumption over there. I mean, I'm sure that will happen over there. So can you incorporate other networks into this? Can you incorporate creating good contracts between utilities and smaller players? I mean, look at here at North Zone. I don't know where this is. I was just searching on Google. A megawatt per hour cost, sometimes around $2,500. I mean, so there are lots of opportunities when you make systems bigger and bigger, especially if you also bring into the picture carbon trading, weather, all together to come up with a good way to predict the forecast the energy needs, not only for your area, but maybe for the utility. Then you may have some opportunities. One other thing that I would like to talk about is actually reliability. How many of you have, or does anybody have any car when you stop, it turns off the motor? I mean, this summer I was in Turkey. Two of my brothers have those cars. When you stop, I mean, one was a Mercedes, the other one was Volkswagen Passat. When you stop at a traffic light, it turns off the motor. And actually, there are lots of these kind of technologies which have been implemented in the United States. Again, instead of keeping your machine idle, you turn it off, okay? Like Benz, this is a Ford, I think this was a Chevy. It is here. I mean, if you go and try to purchase a car right now, you'll have something like this. So, is this good or bad? Why is that? Because when you turn on and turn off so many times, you put additional load, additional stress on the motors. One needs to characterize if reliability versus energy consumption. I mean, where do we stand on that? That is, we really do not have a very good understanding of this, and right now we are implementing this in our daily life in big motors, automobiles. I mean, it will be everywhere. So we need to have a systems perspective on system reliability, energy efficiency, and through a life cycle concept. So some other things that I learned during yesterday and today, and I think which also can be some future research areas is, yeah, we have sensors. Like today I learned that Siemens has done lots of things on this, but do we have an affordable way to implement these technologies everywhere? Do we have good methods, frameworks to perform data analytics on energy consumption sensors, data, especially I mean, I have seen like in Fiat-owned companies, like we have Case New Holland in Wichita. I mean, they try to observe machine-level energy consumption throughout the plant. But I mean, can we? What are we gonna do with that data? And how can you come up with better strategies for turning on and off different subcomponents, and which are really easily applicable? Easily applicable is, I think, the buzzword over there. Again, not too expensive. The fourth bullet is extremely important. I mean, I don't think if we have enough information on reliability data when we try to incorporate turning on and off machines. I don't know if you would agree or not, but at least we couldn't find it. Maybe you were working for Siemens, so you had data, but we couldn't find it. Hmm?
Battery charge and discharge stuff,
Yeah.
stop charging, the charging cycle,
Yeah.
completion cycle, that definitely impact the life. But
Yeah,
it's
so
an analytical model there.
yeah. So I will repeat what you have been telling since I have the microphone. For example, battery charging and recharging has impact on reliability of components. So that is something that came. And then if you would like to incorporate environmental carbon footprint, occupational health impacts into the picture, then what happens? I mean, my last slide is this, so I really wanted to stay in 15 minutes. Hopefully I have done that. So I stole this from yesterday's Michael's presentation. We would like to have data-driven, intelligent, adaptive, automated systems which could benefit us for energy-aware operations planning. So this is all I have. Thank you.
As I get ready to give the little good-looking line to our speaker, okay? If you have any questions, okay, if you could please.
Thank you very much.
That's a good-looking line.
Okay,
And
thank you.
It will look great in your office.
Thank you very much.
Ferocious looking line.
Exactly.
Now my next trip, I mean, tomorrow I'll be going to Florida, and the department chair over there is Penn State graduate, Joe Junis. I was going to show him, but he's traveling as well, so I will just take a picture and send it to him. So okay, thank you very much. And so now is the plan having the panel sit here? Does
That would
everybody?
be great.
Yeah.
And